is Mohammed, and today I'll be talking to you about design of hands-free interface for object relocation. So, about 5.5 million people in the US are reported to have some sort of paralysis. Of these people with paralysis, about 3 million are classified as severely paralyzed in America. They need a way to control objects around them, and this is a problem because it limits their ability to work. The complexity of human-machine interaction. This is a process driven by input from a human user. The challenges with using a human-machine interaction is that the system requires huge amounts of user input and focus, and it's very time-sensitive, so it's not practical for the real world. 2.9 million people who consider themselves as severely paralyzed need a technology that allows them to relocate objects without requiring motion. The design has to assist users in other daily activities that ordinarily rely on physical input, such as navigating a robot to perform a fetch and deliver task. Here's our stakeholder analysis. For control technology companies, these are the people who are designing the alternatives that could be integrated with our product. And we have severely paralyzed, which is our main stakeholder. They'll benefit from this hands-free control system, and the tension with that is the high level of learning time and the initial distrust of system. And for insurance company, this is mainly for the medical insurance. They'll have to create new policies that include the hands-free control system. And for HHS and FDA, since the product is covered under the Medical Device Act, it would require a lot of testing and approval. And for in-home care organizations, this could either fill in the need for the shortage of in-home care, and it places concerns for them being replaced if the hands-free control system is a better way to help them. Here's our stakeholder interaction diagram. So here's our tray space. As you can see, there's methods to perform hands-free control system. There's eye tracking, head movement such as gyroscope, voice control, muscle detection, and brain-computer interface. Evaluate REG, eye tracking, and voice command. Muscle contraction detection and gyroscope will not be evaluated as these alternatives require physical input or movement. So the summary voice command is it has unlimited number of commands. It's a ready-to-use technology, and from a study from School of Information Technology in China, it has a 92% success rate and a 2.2 second average delay. For eye tracking, it's subject to false positives. It solely requires on a lot of calibration, and it's 40 milliseconds slower than using a mouse. Gap analysis is the 2.9 million people who are severely paralyzed need a way to interact with the environment around them by using a physical interface. So our win-win scenario is to create a control system interface which can match the quality and cost of a traditional hands-free interface. What control interface can be selected, we have to know the maneuvers and the statistic of these maneuvers that the robot will perform. So what we're trying to do is create a simulation which collects and analyzes data crucial to creating hands-free control interface. Here's our concept operations. A paralyzed person cannot perform basic motor tasks without assistance. A robot controlled by the user can cross the room and retrieve an item. So here's our functional diagram. The robot is composed of a platform, an arm, and a gripper. It has a camera to feed information to the person in case that he or she cannot turn its head or cannot see the robot. So the robot is controlled by a user interface with a voice command, and the robot will navigate around the room accordingly, and has a collision avoidance system to avoid collision. And it has an automated gripper command, which we'll get to later. In this case, a user gives a task to a robot. The robot from the start position goes to the object. The robot picks up the item and brings it back to the user. Our requirements, our commands for the robot. We're using VREP as a virtual robot simulator, and we're using MATLAB to find the pathing and the amount of degree of turns needed in order for the robot to get an object. So here's our YouBot virtual robot. It has omnidirectional wheels, 0 turn radius pivoting, and surface for placing multiple objects. The arm has 5 joints for 5 degrees of freedom movement, and each joint has limited range of movement. The gripper can open and close. Here are the dimensions of the robot. So the simulation objectives, as said before, is to see how many commands are needed and the statistic of those commands, such as the turn radius, the arm movement, and the gripper commands. Here are simulation requirements. Simulation overview: the robot is randomly placed in a room and is tasked to pick up an item at a random location. So here's the simulation statistics. And here's the inputs. So here are the modules that are created. Generate path creates a path from the robot to the shortest path to the fetch location. Statistic gives back the stats of the movement necessary for the robot to get the item, and graphical data displays the frequency of maneuvers. So here's an example for a single run. As you can see, it shows the distance traveled and the angle of turn and the frequency of those movements. Simulation output for 50 turns. And simulation, depending on the position of the YouBot base, the arm joint positions are different even for moving an object of the same height. An alternative to manual control of arm gripper, a vision sensor can be used to track the object and be simplified by having the user say that he or she wants to pick up object 1 or object 2. Is vision sensor for hands-free control display. As you can see, the robot views an object, it classifies it as a number, and the person says the number, and the robot will pick it up. Simulation results: we need 6 platform commands, which are turn left 18 degrees, turn left 2 degrees, turn right 18 degrees, turn right 2 degrees, start and stop, vision sensor and active algorithm, automated collision avoidance, and return to user function. So the impact of the simulation shows that the hands-free control system shall be capable of differentiating between 9 commands and executing the 9 commands. Decision criteria for designing the alternatives: we have capabilities, TRL, which is technological readiness level, usability, and performance. Under capabilities, we have number of commands and time sensitivity. And under usability, we have proportion of paralyzed population that are able to use it, and the setup time required for the users. For performance, we have accuracy, maintainability, and reliability. Our attribute weights. So here's our utility calculation. As you can see, voice command has the highest utility with eye tracking and BCI following it up. Here's our sensitivity analysis. For the most part, the utility of the criteria weren't very sensitive, but for reliability measure and population measure, voice command has a high utility, but if the weight were to be increased, then eye tracking would have the highest utility. Here's the cost versus utility for 1 year. Brain control interface has extremely high cost and low utility, whereas eye tracking and voice command has low cost but very high utility. This creates is it eliminates the need of a 24 in-home caregiver. It fills in the in-home caregiver shortage and returns the level of independence to these paralyzed people. A unit is defined as a robotic aid plus hands-free control system. We plan on selling it to the in-home care organizations and hope to form a partnership with them. Costs